All right, jumping right back into this, we're over at L5 now. We were asked to go ahead and shade in the region by this dot here for the area under the bell curve. So we know that there is a correlation here between our normal cumulative distribution function and our bell curve. So if we do have a point here, this would be the same area that we're seeing in the bell curve here in conjunction with where we are in the exponential, or in the normal cumulative distribution function rather. So if this dot were to be moved over here, we could then draw a line right down and show that from this point forward, this is going to be the area that's equal to, in this case, if the dot was moved over here, this much data or this far into the normal cumulative distribution graph. They would also be equal. Likewise here, they're equal as well. Here's the area. This is the same area here that we're describing. All right, moving forward here. Identify the point of the normal cumulative distribution function, whose y-slope measures in the shaded area. So there's that point there. Similar what we just did. Now we're just telling where the point is, and the shading was done for us ahead of time. So we kind of reversed what we were trying to do there. All right, L6, we're going into here. What is this interesting thing here, ERF of x? That's interesting. It's actually going to be an error function that we are going over in our homework as well. And this is going to be defined by an integral that can be described by the Taylor series, which we got into a little bit, and how to come up with an error function. This is where the normal cumulative distribution is going to be coming from. So we went and did a little section on working on the normal cumulative distribution function into the Taylor series and came out with that error function. Looking at this new, exponential curves now. So now we kind of flipped them on us a little bit. We are asked to say one of them is going to have a median point at 1 and one's going to be at 3, and has to identify which is which. The median at 1, of course, 1's going to be here in between 0 and 2. So we can tell this one here is going to be 1. Most of the data is going to be around the median, so when we know this one's going to be a little bit higher up. This one, the bottom graph here, excuse me, I mislabeled that one. It's this elongated graph, so bump that one right up just a little bit there. At 3, this is going to be a more easy sloping line because the median is going to be at 3, so we have a lot more even or more spread out distribution of data, because we know that this is going to be an exponential curve, and we have most of our data centered with a median around 3, so we have it more evenly spread out, whereas that median's at 1, all the data is going to be hovering around 1, which makes it very tight and very high of a graph here. So excuse me on that. Let's see if I can. That should be up here. My apologies, that's incorrect. All right. Moving forward here, we were given a relationship between normal cumulative distribution and the bell curve. And so what we wanted to do here, again, we wanted to say, what happens when you have a median of 3.1 and the standard deviation of 0.6. For the clued-in stacks folks out there, we will know that we can make a line from the x-axis to the normal cumulative distribution function. It's going to be the same area measurement as the shaded area under that bell curve. That is the relationship between these two different types of graphs here. L9, communication. We're looking at a normal cumulative distribution function, which is going to have a median of 66 and standard deviation at 4.9. So looking into this, what can we do with this information? Well, we absolutely, for any clued-in person, we will be able to tell them all of the information. We do know that this is going to be a normally distributed data set. In addition to that, we're given extra firepower here, knowing the median and also knowing the standard deviation. So with those pieces of information, we can calculate anything with that type of knowledge there. On the exponential side, so similarly on exponential function, it's going to be a lot of the same things. We don't need that standard deviation anymore for the exponential function. All we need to know is that median point. And from here, knowing that it's an exponential cumulative distribution function in tandem with knowing where the median is, we're going to be able to tell you any type of information about that data, about that graph whatsoever. And I kind of drew over here a really silly graph over here of the exponential cumulative distribution function in its longer form, 1 minus e to the x over m. Again, no reference to the standard deviation whatsoever. We can calculate any kind of percentages on those graphs given that data because we know how it's going to be distributed, and we also know the median point. Looking at averages. So next off, and excuse me for the light again, sorry about that. On averages here, we were shown again our median point and our standard deviation point, and we were asked to say, without any further work, can you tell us, the average of that point? And yeah, of course we know the average, and the average is going to be 66. That's going to be your median point. So I agree with that. We do know that half of that data is expected to be less, and half that data is expected to be more than the median point. On the exponential side, we're given the same question here, and I'm going to give the same answer. I'm going to stick true to it. Agree. If we know that median point, half is going to be less and half is going to be more. So if the median is at 120, we know about half of the data is going to be less and half is going to be more. All right, now let's go through here on some more stuff. We were given out on this type of graph here, we were shown normal community distribution, and then we kind of took out the median point here from every single piece of information here. So what happens there? What are we going to do with that type of information? Well, we're going to know that if the n has been taken out of the equation, we will still know everything that we know about that approximately normal community distribution because, as you can see, as I rotate back up, my apologies, we've taken out that m fully. There's no more m in this function whatsoever. So if they're going to go through with that type of calculation, then it absolutely will work, and it'll be exactly the same. Similarly, down here at the bottom, we're given an exponential function. Again, same thing. We took out the m, and we actually took out the sigma as well. So sigma is going to equal to 1, and that m is going to be taken out completely. So with those two fully removed, we can go ahead and approximate those normal community distributions just the same. Looking forward here, so we're asked then to say, oh, we have a new normal community distribution of mu plus s sigma when q sets that value. So we know that when the s is going to be subbed out for that mu plus s sigma, that the m and the mu and the sigma are going to be flushed out of that equation totally. So that kind of nullifies it, kind of makes it more generic so that we know exactly what to do with it. And we actually don't even, it gives us a lot more power because we're able to calculate those things without having to deal with x. Or, yeah, deal with x. Nobody likes x. All right, closely packed around the median point here. So we know here we're asked to say, what does this data give us? We do know the median is going to be 13.7. We know that the standard deviation is 0.4. So yes, I agree. The standard deviation is a very small figure, 0.4. So yes, a lot of the data is going to be huddled around that median point of 13.7. Conversely, we have the same thing, 13.7, and the standard deviation is 20.9. It's huge. So I'm going to disagree. This sigma is going to be large, so you know that data is going to be very spread out across the graph. Very, very far spread out. It's 20.9 as a sigma. When you have a median point of 13.7, you're going to be flying all over the place, left and right on that graph. Closely packed around 0. So we have here a median point of 0.5, and what would happen there on an exponential function? I agree, it's all going to be packed around 0 because we have a median of 0.5. So here's my awful graph again. We have a median here of 0.5. So from there, we know that most of the data is going to be right around 0.5. That's the median point here on an exponential function. And so, yeah, it's going to be definitely most of that information is going to be somewhere in this between 0 and 1, let's call it, just for sake of ease, on that kind of graph. Yeah, and I kind of drew it kind of like 0.5 and 0.75, but you get the idea. So, yeah, all that information is definitely going to be right there in that crux of that graph. Then we're looking at a exponential distribution. Our median is going to be 169. So when we see that on our distribution 169, it asks us what's our expected lifetime average. Our median is 169, and it was given there in the question. Then we said when t equals 100, we have an expected failure rate of 44%, which means that 65% of them are still going to be working. And then we were asked about what's the probability going to be working after another 100 units. Well, when we put that into our little machine there, 200, we then pop out a 0.69377, which means, you can flip it over, about 30% of those machines are still going to be working after 100 or 200 rather time units. We don't know what that's seconds or minutes or whatever. It's a time unit. Similarly on the normal distribution, we're then given our median here. We're expected the average lifetime is again, it's going to be our median, 140 units. And then from here, we were asked to calculate what happens if we know that after 150, which our median is 140, so after 150, we have a pretty large percentage of functioning flowers still. Flowers, they're functioning. It's ridiculous. So then we can go in here and say after another 150 time units, what happens? Well, actually our standard deviation is only 20. So if we go another 150 time units, we're actually going to t equals 300, which is kind of ridiculous. That's 8 standard deviations away from the median. So very few, if any, our flowers are still going to be alive after 8 standard deviations out from the median life expectancy. That's a lot to ask of a flower there. So very few, if any, would still be alive. And then we're asked here to look at the bell curve function here and find its derivative and find out what the sigma equals here, the final thing here. So we took this function, and we've kind of gone through this before in our homework sections, but when you take the derivative of x of n, we're just going to be left with n. So that's going to be equal to 1. So our standard deviation, or sigma, is going to be equal to 1, which we were given right here. Love it. All right, and that is our literacy sheet for normal and exponential functions on the PSLM 5. Thank you.